Okay, it's my pleasure to give this talk here to you guys at SAAO. What I'm going to talk about will have two parts today. So the first part will be about the interstellar medium physics, and it's about the new progress that we have made in constraining more accurately the photoionization models of star-forming regions. And then the second part of the talk will be about a new instrument and project that we are developing that will map the interstellar medium at scales between sub-parsec and hundreds of parsec to help us understand the feedback of star formation. So let's start. So the science is about star formation, and we really want to understand how star formation is triggered and how it is stopped in galaxies, because this is a very fundamental and very major activity in galaxy evolution. Stars light up the universe, they form heavy elements and make life possible. So it's really important for us to understand how they were formed and what controls the efficiency of star formation. This is the famous picture from MA2 showing you the feedback process of star formation. So the key question we want to understand is, why is star formation so inefficient? And this statement is actually have evidence from many different threads, so that here I'm going to show you two of those. The first one comes from cosmological large-scale structure studies, and we know that the mass function of dark matter halos is a power law function. This is that curve. And then if you have a constant baryon fraction in dark matter halos, then the baryonic mass function of dark matter halos is also a power law. But the stellar mass function of galaxies is a Schechter function, and that has very different shape. And what this means is that the efficiency of turning baryons into stars is not the same in all the galaxies. It is most efficient at this intermediate mass, but at both low mass and high mass, the efficiency is low. Why is that efficiency low? We think it is due to feedback from star formation and supernova in low mass galaxies and from AGN in high mass galaxies. And there's many evidence for this, such as the figure I just showed you earlier, that the picture from MA2. However, the details of how these feedback mechanism working is not completely clear. There's many detailed physical processes is unclear. So that anyway, this shows you the star formation is inefficient in some galaxies. Another line of evidence comes from detailed spatially resolved structures and from molecular cloud observations. And if you look at the star formation rate surface density as a function of the molecular gas surface density, you find they're very, very well correlated. And that correlation suggests that the molecular gas depletion time is about a few gig-years in most cases. And that is 100 to 1,000 times longer than the free fall time of a giant molecular cloud. Why is star formation so slow compared to our theoretical expectations? And why is it so inefficient? We think it is due to feedback, but exactly how does that feedback works is not completely clear. And this is the central question that we want to understand. And to understand that, we have to study the interstellar medium, because the interstellar medium is a very central component of galaxies. It is where stars are formed, and it is also the deposit of the feedback energy and the mass lost by stars. They're deposited into the ISM. The radiative energy and the kinetic energy are also deposited to the interstellar medium. Stars can also, the feedback can also push gas out of the galaxy into the circumgalactic and intergalactic medium, from which they can also accrete back to the galaxy, and that also mix into the interstellar medium, from which future generations of stars are forming. For the AGN feedback, it's the same process, a similar process. AGN accretes material from the ISM and also give the feedback energy and material back to the ISM. And also the jets and outflows can go out of the galaxy and accretes back to the ISM. Anyway, the ISM is a very central component. And so that understanding ISM is very important for understanding the feedback from star formation and AGN. There are many different components of the ISM. There's neutral gas, atomic gas, molecular gas, and ionized gas, both warm and hot. And there's all these different phases are very important, and we need to study them from multi-wavelength observations. But my interest has always been about the warm ionized gas phase, because it's a very stable phase of the ISM under both photoionized and collisional ionized conditions. It is near the peak of the cooling curve. It's relatively easy to observe and has very well developed land ratio diagnostics and has been studied for many decades. And it's a very mature field. However, there's still many mysteries and discrepancies about this phase. What mysteries and discrepancies are there? So first of all, there are two classes of commonly found but poorly understood warm ionized gas. The first is called the diffuse ionized gas, and this is found in our Milky Way and in other star-forming disk galaxies. This picture on the right shows you the H-alpha map of the Milky Way, and you can see the galactic planets here. In the galactic planet, there are these big star-forming regions and supernova remnants, and that's where the H-alpha emission is strongest. But outside these regions, you also have a lot of H-alpha emission. And this is a so-called Reynolds layer. They can be seen above and below the disk and in between star-forming regions. What is ionizing these gas is not completely clear. In external galaxies, we can see a similar thing, is that in this is star-forming galaxies with spiral arms, and you can see the star-forming regions dotting the spiral arms. By the way, this is a narrowband H-alpha image. But in between the star-forming regions and in between the spiral arms, you can also see H-alpha emission. This is a diffuse ionized gas. This is seen in almost all star-forming galaxies. And that diffuse ionized gas can contribute about 50% of the total H-alpha emission in a typical star-forming galaxy. And so that understanding them is very important. It's a very important contributor to the ISM, component of the ISM. In another type of galaxies, in elliptical and lenticular galaxies, you also have these kind of a kind of low ionization gas. And this is a spectrum of elliptical galaxy. Actually, this is a stack spectrum of many elliptical galaxies. So you have very high Higgs noise. You can see the stellar continuum really well. If you can carefully subtract the stellar continuum away, you found that these elliptical and lenticular galaxies also have low ionization gas in them. And these are actually not due to the central AGNs in the center. And you found that these lines are weak, but their line ratios are very similar to a type of AGN called Lanners. So that's which Lanners stands for low ionization nuclear emission line regions. And so these type of gas can be seen not only in the nuclear region, but also in the regions outside the nuclear region. As you can see in extended spatial distribution in galaxies. So we quite often call them Lanner-like, or sometimes we remove the word N and call them liars, low ionization emission line regions. And exactly what is, whoops, sorry. Let me close this. Okay, you can see my slides again now, right?
Yes.
Yeah. So in these galaxies, they have these Lanner-like line ratios, but we don't understand what is producing the ionization, what is causing these guys to be ionized. We think it is maybe post-AGB stars, or maybe some other collisional ionization mechanism that is causing the gas to be ionized, but we don't fully understand. So for both DIG and these liar gas, that the ionization mechanism is still a puzzle. And we have done a lot of work in this direction, and I'm very happy to talk to you about these topics. But today, I'm going to talk about a well-known phenomena in star-forming regions. We think that we understand the ionization mechanism in star-forming regions. However, there's also discrepancies about those. And one of that is about how to measure elemental abundances. Elemental abundances of star-forming regions is very important. This is the famous mass-metallicity relationship. This is stellar mass, and this is metallicity. Using the Sloan data and many other surveys, we have found, people have found that there's a very good correlation between the two. And using this relationship, you can derive the effective yield of galaxies, from which you can understand how much gas is flowing in and out of galaxies. And that is very important to understand galaxy evolution. But how to measure this metallicity is actually a problem. The plot on the right shows you the spatially resolved mass metallicity relationship that we derived using manga data. You can see this spatially resolved metallicity versus a stellar mass surface density is also a very good correlation. And people try to understand how the scatter in the mass metallicity relation depends on other properties, based, for example, star formation rate. And that is very important for us to understand how the interstellar medium is enriched. However, that the metallicity measurements have a lot of discrepancies in the literature. Even if you use the same data, but just applying different metallicity calibration methods, as indicated by these different labels, these are all using different line ratios and using direct methods or using strong line, some are using weak line, just different methods. And you find they give you very different results, even if you're using the same set of data. And that is unacceptable. This change can be a factor of 10 from the lowest to the highest. And that if we cannot constrain metallicity to better than a factor of 10, then how can we understand the enrichment of the ISM? On the right, I'm showing you the nitrogen to oxygen abundance as a function of oxygen to hydrogen abundance presented by these papers in the literature. Nitrogen is a secondary element, so its abundance relative to oxygen is actually not a constant versus metallicity. It actually gets higher as the oxygen abundance gets higher, because in stars that are pre-enriching metals, the production of nitrogen is more enhanced. However, exactly what is this prescription is actually very different by different authors. If you use these different assumptions in your photoionization models, you would get very different results, and that will result in these kind of discrepancies. So why do we have these discrepancies after many decades of work on trying to derive metallicity? To understand that, we need to review how we do photoionization modeling. To model a photoionized cloud that is photoionized by young stars, you start with some geometric structure. You have a star that's shining radiation on a cloud. The cloud initially is neutral. If you give the input spectra, if you given a spectrum from the star and density of the cloud, you can model how the radiation propagates through the cloud, and from which you can use ionization balance and thermal balance to derive the ionized cloud structure. You will get which region of the cloud is ionized and which region is neutral. And for different elements, you can model different stages of ionization and figuring out how they're distributed, from which you can predict the strength of the emission lines. And then compare that with the data, you will understand what is the metallicity and what is the ionization parameter, meaning how strong the radiation is. However, that these photoionization models have many assumptions behind it, and many of these assumptions are under-tested. For example, the input ionizing ICD can have many different choices, that people can use different stellar population models and consume different star formation history or different ages, and you get different results. And no one knows which one is better than the other. And people also assume different elemental abundance patterns and different secondary elements prescriptions, such as that for nitrogen, and dust depletion pattern is very poorly constrained. And also the geometry and density of the cloud can vary. given all these different assumptions that people make, it's not surprising that why we have such a wide range of discrepancy in metallicity measurements. So how can we do better? We actually need to constrain those under-tested assumptions. We need to make to first settle those in order to make progress. And one important tool is these line ratio diagnostic diagrams. This is a very classical thing. You probably have seen this a lot of times. This is also the so-called BPT diagrams. It plots two sets of line ratios versus each other. This is oxygen 3 to H beta ratio versus N to H alpha, or versus sulfur to H alpha, oxygen 1 H alpha. These diagrams are very good at separating different classes of objects. However, I want to say that these two-dimensional diagrams have significant drawbacks, and that is actually limiting our progress. One of the drawbacks is that when you use these BPT diagrams to do classifications, the demarcations that people use are just completely empirical. They're not well motivated theoretically. For example, these curves that people put down are just put down by hand, kind of arbitrarily. It's not actually based on theoretical models. And some curves are indeed based on theoretical models, but it actually doesn't match the data that they were intended to match. And also that classifications of objects in this diagram can be diagram dependent, and that leads to a lot of ambiguity. For example, a galaxy that is classified as AGN in the N to H alpha diagram can become a star forming galaxy in the sulfur to H alpha diagram. And quite often when people do this, they just throw away those ambiguous objects, and that just leads to sample bias, right? And also the nature of the region in between the star forming region and AGN is unclear. This region is usually called the composite region, or the mixing sequence, or an intermediate region. But exactly what they is unclear. Some say it is composites of two things combined, and then others say maybe it's just a low ionization AGN. And how to decompose them is also unclear, is ambiguous, because it depends on where do you put the starting point, right? So this is a big problem. And the way we want to solve it is actually to look at multiple line ratios simultaneously, not limit ourselves to two-dimensional diagrams, but go to higher dimensions. And the data we are using is coming from the SASS4 MANGA survey. MANGA stands for Mapping Nearby Galaxies at APO. It's a survey that we have already finished 2 years ago. We did multi-object integral field spectroscopy of 10,000 nearby galaxies and obtained a huge amount of data with a spatial resolution of 2.5 arc seconds, which corresponding to 1 to 2 kpc in these galaxies, with a spatial resolution of 2,000, spectral resolution of 2,000, and covering the complete optical wavelength range. And these are some example maps we have for showing the kinematics of the galaxy, the emission line distribution, and the stellar population distribution in galaxies. The data are completely released to the public, and you can play with it. So that is the data that we are using in these graphs I'm going to show you next. This work is done by my student Xihan Ji and myself. Xihan is a very smart graduate student and is going to be on the job market in the coming year, so you should watch out for him. So going back to the problem, we want to resolve the discrepancies between different BPT diagrams. So the best way is to look at the distribution of the data versus the model in three-dimensional line ratio space. So here I'm constructing a three-dimensional line ratio space composed of O3 H beta, sulfur to H alpha, and N2 H alpha ratios. All three line ratios are insensitive to dust. So these are the three famous line ratios that are often used in BPT diagrams. And when you plot them in 3 dimensions, you see that the 3 dimensions help you to make sure that you are looking, if you have a model that is matching the data point, it is consistent in all 3 line ratios simultaneously. You can see in the 3 dimensions, the data points, it also show you a star forming locus and an AGN branch. The data, the model grids that we have been plotting previously, I didn't discuss that. That was generated using the cloudy photoionization models, in which we vary the metallicity in one dimension and ionization parameter in another dimension. So that gives you a two-dimensional grid. What at these things in the traditional BPT diagrams, you will see those model grids wrap around it on itself. But in the three, a curved surface. And what you want is that the curved surface should go through the data points. And then you know that the model is consistent with the data. And this blue model surface is the star-forming model surface, and it actually correctly goes through the data distribution, the data locus. And then the Aegean model surface is a gray surface, and it envelopes the upper part of the data. And in the 3 dimension, you can see it's actually very easy to see which data points are consistent with the model and which are not. For example, in this angle, you can see those points that are in between the Aegean and the star-forming locus. They're not consistent with any of these models. The only way to explain them is actually to make them a combination of the two models, right? So you have an Aegean combining with the star formation. So indeed, those are composite objects. So this becomes very easy, very clear in this 3-dimensional diagrams. And also you can realize that the best way to judge whether a model is consistent with the data is try to look at the relevant part of the model surface from an adjunct perspective. The model surface is curved, so it cannot be perfectly adjunct, but a large part of it is not populated by the data at all. You only care about the part that is populated. And if you just focus on that part, you can make it adjunct, and that is the best way to judge what is consistent and what is not consistent between the model and data. So we want to find the adjunct viewing angle in which that we can see both model surface from an adjunct perspective. So this is the model surface that the projection that we found. This is best viewing angle. The relevant part of the Aegean model surface and the star-forming model surface are both viewed from an adjunct perspective. And we can reproject it to 2 dimensions for our convenience. Now in this new 2D reprojection, the 2 axes are now linear combinations of the previous 3 axes. And here this N2 and S2 and R3 are just shorthand for these 3 log line ratios. And we can also drop a lot of these other irrelevant model surface. But let me just show you the data distribution by itself. And you can see this is the star-forming locus. And now it's viewed from an adjunct perspective. And this is the Aegean blob. There is indeed a concentration over here. And the region in between the two is actually underpopulated, which makes a lot of sense. Because if these things are indeed due to a combination of the two, it's actually very rare to have equal contributions in terms of emission lines. That more often than not, you have one phenomena dominating the combined line ratio, so that quite often you have points that are close to the star-forming surface or close to the Aegean blob, but rarely it's exactly half-half combination. And so here is the relevant part of the model surface. If you use only that relevant part, you can see it is completely adjunct. And in this perspective, it's very easy to judge what is consistent, whether the model is consistent with the data. The star-forming model is doing pretty well, but the Aegean model actually does not do very well. This fiducial model we use covers the red edge, but it actually does not go through the densest part of the Aegean blob. That means this is not the most typical Aegeans in the universe. So with this reprojection, we can now interpret the axis, the y-axis here. This P2 axis is basically a proxy of metallicity, and this is the mixing direction. You can also look at the dimension that is perpendicular to P1 and P2, and that is a proxy for ionization parameter. So P3 is perpendicular to P1 and P2. So this is seeing the model surface from a face-down perspective. So now with this reprojection, it is much easier to constrain those under-tested assumptions. For example, the nitrogen to oxygen prescription that we have before, that different authors give different prescriptions. Now, if you use them to build photoionization models and plot them in this diagram, you can see it's very easy to tell which model is correct. The Dalpita sorting model provides the correct matching to the data, but the Groove's 2004 model actually is completely offset from the star forming locus, and that is not the correct model. Using the Dalpita sorting is much preferred for star forming regions. And in the AGN region, though, you find that the Dalpita sorting doesn't reach the bottom part of the AGN blob. And that is actually saying that in the AGN regions, the N2O prescription may be higher than that in the star forming region. This is a new puzzle that we can see. But anyway, this shows you how well you can constrain the models. You can also constrain the input spectral energy distributions. For example, for AGN, you can use different power law index, and that will correspond to a very obvious shift in the position of the model locus. And you can see that our fiducial model isn't the best, but if you make it a little bit softer, that model will give a much better prediction for the majority of AGN dominated cases. And also that these models correspond to different ages for the young stars, and you see that the younger models actually do better than the slightly older model. So that is a significant progress that we made so that we can use this reprojection to constrain all the assumptions in photoionization models. But not all the models in the literature are consistent with the data. That if you look at other models that are people publish in the literature that are very widely used, they are not always consistent with the data itself in this new projection. And it's very easy to tell. You can see they have different curvature. They're not matching the star forming locus. And if they don't match the star forming locus, they will lead to discrepancies when you use different sets of line ratios to constrain metallicity. So this shows you the Dalpita 2013 model. Although it gives you the correct N2O prescription, there's other assumptions in it that are causing it not to match the data locus in this P1, P2 projection. And using this model, if you use different sets of line ratios to constrain ionization parameter and metallicity, depending on what line ratios you use, you get very different results. If you use these three line ratios, you get this U-shaped curve. And if you use these two other line ratios, you get a very flat curve, flat correlation between the two parameters. And that's just self-contradictory, right? But if you have a model, and also this shows you the one-dimensional distribution of metallicity and ionization parameter that you can obtain when you use different sets of line ratios. You can see they're very different. Some line ratios will give you a double-peaked metallicity distribution, but other line ratio will give you a single-peaked metallicity distribution. So this is causing discrepancies because the model is not consistent with multiple line ratios at the same time. But if you use the correct model, the model that we make in this paper, and you will see that it gives very consistent predictions between ionization and metallicity, no matter which line ratios you use. And we found there's a positive correlation between the ionization parameter and metallicity. And that is actually contradictory to what the theoretical models predict. The theoretical model actually predicts a negative correlation between the ionization parameter and metallicity. But anyway, here we get totally consistent prediction no matter which line ratios we use. So I think this is the correct correlation. So that now it's a serious problem to understand why it is a positive correlation. And again, in one dimensions, you can see the prediction will make very consistent no matter which sets of line ratios you use. Although there's still a small discrepancy, and that is related to a dust correction problem I'm going to talk about in a little bit. There are other emission lines that we can look at in the optical regime, and some of the lines are very inconsistent with our models. Even our best fitting models cannot predict the oxygen 1 6300 line correctly. So in this projection, we have replaced the sulfur 2 line ratio with the oxygen 1 line ratio. And in that, you can see the data locus is like this, but the models are curved, and it's not predicting the oxygen 1 line ratio correctly. Similarly, if you replace the OSH beta with the sulfur 3, sulfur 2 ratio, you also find a big shift. Basically, the current models are under predicting oxygen 1 by about a factor of 2 to 3, and over predicting sulfur 3 by a factor of 3. And these discrepancies, we haven't found the way to resolve that discrepancy. Some other assumptions that we are making in the models are actually incorrect. But this shows you how strong the constraining power is of the data. The data have so much constraining power that gives me hope that we can achieve precision gas astrophysics in the same style as precision cosmology. And just like in cosmology, you have very good model, and so that just you can use different data to put constraints on different cosmological parameters. Here we have our roadmaps that to help us go towards precision gas astrophysics. The first thing we need to do is to identify and fix those problematic lines and find out which assumptions we need to change in order to fix those emission lines to make sure they're consistent with other lines as well. And then we can establish a metric to quantify the consistency between the data and the model surface in higher dimensions. And once you have that, you can just simply parameterize the input assumptions, the spectral energy distribution, the interval prescription, the dust depletion pattern, and then you can constrain the average values and identify the source of scatters. You can also look at the scatter as a function of other secondary parameters of the photoionization models. And so that will help us to unify the metallicity and ionization parameter measurements and to get more accurate star formation history and baryon cycling history and better understanding of feedback. So this is our ultimate goal, that we want to work towards this direction, but also that we also need to make our photoionization models better. The current photoionization model is very simplistic, that it's a one-dimensional model actually, and it's assuming the gas cloud is uniform. However, the actual regions are very complex. As you probably have seen from the recent picture released by JWST, the actual regions are very, very complex. And there's a lot of non-uniformity, inhomogeneity in actual regions. The density is not homogeneous, dust distribution is not homogeneous. So that there's a lot of complexity that we actually need to understand. Here is one example of that, is that we actually, using this three-dimensional diagram, we realize there's a new way to constrain the dust attenuation curve using forbidden lines rather than Balmer lines. For example, here is, again, this three-dimensional diagram. Because these three-line ratios are insensitive to dust, we can use a tiny bin in the 3D space to find a sample of star-forming regions that have the same metallicity and same ionization parameter. Once you fix that, you know all the other intrinsic line ratios should be roughly the same as well. And the biggest discrepancy, the biggest variation that will be introduced besides metallicity and ionization parameter would be dust attenuation. And if you look at all the points in that in a tiny box in this space and plot a dust-sensitive line ratio, such as the N2O2 ratio, these two lines are widely separated in wavelength space. You plot that as a function of the Balmer decrement. You actually get a way to constrain the extinction curve. And you just need to fit these points as by a linear relationship, and that slope corresponding to the slope of the corresponding to the derivative of the extinction curve. And so the K value here is the total to selective extinction at these different wavelengths. And that is determined by the extinction curve. So you can see whether the slope matches the galactic extinction curve that we often use. We found that it actually does not match, that the extinction curve, this slope we found is actually much shallower than what you use for in galactic extinction curves. For example, the best extinction curve is the Fitzpatrick 99, and that is still over predicting how much correction you can make. This axis is the observed N2O2 ratio minus the intrinsically predicted N2O2 ratio based on the ionization parameter and metallicity constraints. And you find that this slope is shallower than the Fitzpatrick prediction. If you use the Fitzpatrick prediction to correct the N2O2 lines, you find that the results you overcorrected, and the resulting line ratio difference is still a function of Balmer decrement. That shouldn't be, because this line ratio difference should not depend on attenuation. And if it depends on attenuation, that means you are overcorrecting the extinction. So they have a negative slope here. And so does that mean that we simply need to update the extinction curve? That is not the case. Updating the extinction curve doesn't work. The reason is some lines are consistent with the galactic extinction curve, but the low ionization lines appear to show a much flatter curve than the Balmer lines and high ionization lines. So what is going on is that somehow the low ionization lines are behaving completely differently from the Balmer lines and high ionization lines, and also they break a fundamental assumption, a fundamental belief of the attenuation curve being monotonic in the optical wavelength range. What we found is that this derivative between N2 and O2 is actually smaller than that between H alpha and H delta. So N2 and O2 is more widely separated than H alpha and H delta. The difference in extinction between them should be larger, but not smaller than the H alpha and H delta. Right? So, but however, we found the opposite results, and that breaks the widely used assumption that we can use the Balmer decrement to correct other forbidden lines for that extinction. What is going on? What is causing this? We believe that the reason is because that we are using low spatial resolution observations. And when we use low spatial resolution observations that cover a kiloparsec, we are suffering contamination from diffuse ionized gas. And if you use high spatial resolution observations, such as what we obtained by MANGA in IC342, this is a very nearby galaxy that is an ancillary project to MANGA, you can see that there is actually a correlation between the line ratios and the attenuation. That these are H2 regions in the IC342, and these H2 regions have high degree of ionization. They have more in the H2 regions, the high ionization lines are stronger. In the diffuse ionized gas regions, the low ionization lines are stronger. And there is actually also there's a correlation with the amount of attenuation in these different regions. DIG have low ionization, but they also have low amount of extinction. H2 have high ionization, they also have high AV. So which is why that the N2O2 ratio lines, or all the low ionization lines, are seeing less attenuation than what the Balmer lines see. And so the extinction correction becomes invalid in low spatial resolution data. And so this is actually a very serious problem that a lot of extragalactic studies don't have superb resolution as what we have in the Milky Way, right? It's all on kiloparsec scales or even worse. How do you do extinction correction in those integrated data is a problem we have to resolve. And to understand that, we have to understand what this correlation is between the degree of ionization and the level of extinction. And to do that, we need higher spatial resolution to resolve the substructure of H2 regions and their surrounding diffuse ionized gas. This and many other things require us to obtain new observations that to understanding the microstructures and to also to understand the microphysics of feedbac. Feedbac is very important in galaxies, but it's happening on very small scales. And in most large-scale simulations, these are all putting by hand. Those are the subgrid physics. But exactly how those work is not completely clear. How does the small scale physics propagate to large scales? What we want is to measure the temperature density, ionization fraction, dust extinction distributions in actual regions, and also measure the bulk velocity and the turbulence, try to constrain the momentum kinetic energy outflow, and map the magnetic field lines. And also that these observations have to be done on a scale between sub-parsec and hundreds of parsec, because the physics are happening on very small scales below a parsec, but the actual regions and molecular cloud are of the order of tens of parsecs. And in exogalactic observations, we have 1 to 2 kiloparsec observations. We have many famous scaling relationships that are established on this scale, but how they were produced by small scale physics is not clear. The intermediate scale between 0.1 and 100 parsec is the part that is missing. So we need to bridge the small and large scale observations in, for example, the problem is that objects in the sky are either too close to us or too far away. In Orion cloud, 1 arc second is like 0.02 parsec, but in an external galaxy, 1 arc second is 170 parsec. So to obtain observation bridging these scales requires very large mapping area in the sky, and if you can map the complete Orion cloud. This is like half a degree in size, and you need to develop a new instrument to do that. So we are trying to do this, trying to resolve 0.1 parsec, but also cover 100 parsec. And that is difficult to do without achievable by existing instrumentation on large telescopes. Because to resolve 0.1 parsec in the Milky Way doesn't really require a large telescope. A small telescope will actually do better. So because you don't need super angular resolution, since the actual regions in the Milky Way are very, very close. But to cover 100 parsec at that resolution requires a huge dynamic range in spatial coverage versus spatial resolution. To get the huge dynamic range, you need a very large number of spectrographs. For example, BLT Muse has a 24 spectrograph, and that can only reach a dynamic range of 120. You want to reach 1,000, not only we have a large number of spectrographs, but also a dedicated survey instrument. And that is the only way to really probe this scale. So how do we do that? And what other requirements are there? We need a moderately high spectral resolution so we can resolve the ionized outflows on the order of 20 kilometers per second to differentiate different feedback mechanisms. Also, that when you have that high spectral resolution, you can actually measure the temperature of the gas and the turbulence of the gas by you comparing the line width of different atomic species. Because sulfur is heavier, as a heavier element, it will have less burdening compared to hydrogen, and that difference can tell us the thermal burdening versus non-thermal burdening. So the science requirements for this new instrument we're developing is to spectroscopically map the scale between 0.1 and 100 parsec in the Milky Way, and if you apply that same angular resolution in slightly more distant objects in LMC and SMC or M31, you can probe progressively larger scales, but so that you can go all the way from sub-parsec to kiloparsec. And we need to resolve 20 kilometers per second in velocity, and that requires a spectral resolution larger than 15,000. And we need an array of integral field spectrographs paired with small telescopes. So this is what we are imagining, that we want to map these star-forming regions using an array of telescopes paired with an array of spectrographs in a similar style to the Dragon telephoto array. This is not our instrument, this is a Dragonfly telephoto array, but we want to do something but pair it with an array of spectrographs. But we need to make the spectrograph very cheap. We need to make it very cost effective. And to do that, we are using cinder fibers And that allow us to take advantage of technology advancements in CMOS sensors and lens coatings. So we can use many off-the-shelf components for the spectrographs to reduce the cost significantly. CMOS have now gotten really good. They have very low renoise and very deep profile depths. And so they can be as good as CCD, also very, very efficient in the optical regime. And these commercial lenses are also getting superb coatings, and so that they're very efficient. So these technology advancement can help us to build this new instrument called AMAZE. AMAZE stands for Affordable Multiple Aperture Spectroscopy Explorer. And right now we are building the prototype. It's a 547 fiber bundle using 50 micron fibers, and that's corresponding to about 26 arcseconds resolution on the sky. And we covered these two wavelength windows, covered all the important emission lines with a spectral resolution of R15,000. The telescope is a Canon telephoto lens, and the fiber bundle will cover about 20 arc minute across in the sky, and will have a field factor of 31%, covering 79 square arc minute at a time. And we will have a calibration system that provides accurate wavelengths and flat field calibration. Here is how our fiber bundle looks like. And I mean, this is not the bundle yet. We are still making it. And this will, if you can build this, you can cover the Rosetta Nebula in just 19 pointings completely. And you can still resolve sufficient details to understand the subgrid physics. And so this is what we want to do. You compare our instrument with other integral field spectrographs in the world, you can see that the maze is situating at a special place. I think now I actually needed to add the new instrument by Matt's group that is put on salt. Actually, I should add that before the talk because that just came online, I think. So we should add that. But anyway, this plot is showing the spectral resolution as a function of the spatial dynamic range covered by each instrument. Each bar represents an instrument. The left side is its spatial resolution. The right side is spatial coverage. This is in arcseconds. And the top scale is the corresponding physical scale at a distance of 2 kiloparsec. You can see the majority of integral field spectrographs are covering very small angular scales and very small physical scales. So they cannot cover large areas on the sky. And the maze is situating at this special place. And SDS5, large local volume mapper, is also trying to do the same thing, but they have a lower spectral resolution, but a wider wavelength coverage. So these two would be very complementary to each other. We really need both data from both to understand the ISM. So we have tested the instrument in the lab with help from Matt's group. And now this shows you the expected sensitivity of the instrument. In terms of intent-due per dollar, the AMAZE-P is actually 60% more cost-effective than a DESI spectrograph. We are working in very different spectral resolution. So we have much higher spectral resolution, but much lower bandpass. But in terms of intent-due per dollar, we are actually more cost-effective. So if you build many of these spectrographs and using the same cost, you can actually be more efficient than the many DESI spectrographs. So the spectrograph is also relatively cheap. Each spectrograph only costs about $200K US. So if you can build an array of these spectrographs, you can, with a relatively mid-scale project, you can map a quarter of the sky in 4 years, probing down to the diffuse ionized gas. And also the system is very scalable. Right now, we are trying to build two sites, one in the north and one in the south. We have already obtained funding for hardware for 2 of these systems, and the one in the north will probably put in southwest of China, and the one in the south, we're still looking for the site. And SAAO may be a potential site. If you have a place on the mountain that we are very interested in putting our small array there. The only thing we require is just a very dark conditions. And also they need to have small telescopes that are that we can piggyback on, that we can also make, we can go to science faster to do this. So that's it. That's the summary of my talk. That the warm ionized gas is a very critical component. We have developed a new methodology to constrain the photoionization models, and now we have high hopes on this methodology, and so to give us much more accurate models in the future. But new instruments will be needed to give us the small scale observations. Thank you. That's it.
Thank you, Renbin. Thanks for the talk. We have one question. It's not a question, but it's a comment in the chat. I'll just go through that first before asking if you have questions directly asking Renbin. So the comment is, since agents
I can see it.
Yeah, you can see it. Would you like to point it out?
Yeah. So I think what you're commenting about is that since the agents are variable, that in the P1, P2 diagram, the AGN would move. But these are the narrowline regions, because we're not talking about the borderline region. Borderline regions will see more variability, but the narrowline regions are much further away from the nucleus. So they're on tens of parsecs, so that on small scales, sort of on time scales less than 30, 40 years, we don't expect to see variabilities in narrowline regions.
Okay. Then let's go to the questions we have. So first we have Hartmut. You want to ask the question?
Yes, yeah. Thanks very much. I mean, you covered a lot of things that I've often puzzled about and wondered about, and I think every time a question came up, like I had one about how do you deal with the reddening, you came up, you explained that. I really like the way you combine the various line ratios to come with a way of separating between the different classes that looks a lot better than the BPT and Cooley et al. And so on have come up with. Because I find that even then, what seems to always be the issue whenever you try and use that classification method just by looking at line ratios, you very often go to actually look at the spectrum and see that, oh, but hang on, it's quite clear what happened here. It's actually a mix of this and that, and you find that there's different components almost that are sitting next to each other. So my comment or question would be to test whether certain models are actually correct or not. Might it not be better to put more effort into separating the different components? Because if one just looks at line ratios, one gets an aggregate of various things. And it wouldn't maybe the way to go about things is to get really high resolution spectrum of a few selected objects where you can really separate or attempt to separate okay, this is definitely starburst, this is definitely something else, and so on, and check the models this way.
By high resolution, do you mean high spectral resolution or high spatial resolution?
Spectral resolution, yes.
Spectral resolution. So, yes, in the Milky Way, it is possible to do that because, in system where the gas is not too turbulent. But in extragalactic observations, when your spatial resolution is low, when you are looking at it on 1 kiloparsec scales, many different components are mixed together. The diffuse ionized gas and the H2 regions are mixed, and there can be multiple H2 regions in one spatial resolution element. And so that they can have different velocities, and the turbulence in the interstellar medium may make them inseparable, so that it's not necessarily getting high spectral resolution would solve that problem. Is that we quite often see they have 20, 30 kilometers per second velocity dispersion, and that is actually higher than the intrinsic velocity dispersion that you are seeing in an individual actual region. So it's because it's a combination of things. So not only you need to raise the spectral resolution, but also that you have to go for higher spatial resolution. Then it becomes sort of try to reduce the number of components that are projected in the line of sight. Then it is possible. I think, yeah, I agree that then it will be possible to separate them. I think actually one good example is the disk mass survey that also done by Matt Bershedi's group, and they're looking at even more nearby galaxies where they have better spatial resolution and also very high spectral resolution. Then you can indeed see the intrinsic line width. And in those cases, yeah, I agree that you will be able to separate much better. That's true. But in quite often in extragalactic observations, you don't have that luxury, right? It's difficult to do high spectral and high spatial resolution observations. So that, which is why we do a maze, is that then we can really see the individual components by itself and understand it.
Yeah, the reason I was saying that, because very often, say you look at a strong line like the oxygen 3 line, you can literally see how it's not just a simple Gaussian, it's sort of made up of different parts. And I just thought that getting a higher resolution spectrum will allow you to sort of nail down the various, whether it's Gaussian or whatever you fit.
Right, yeah, I agree, yes. That's right, because that's a good point. Quite often you see that in O3 because they sometimes have a wider component and a narrower component, and the wider component probably come from the diffuse ionized gas, and the narrower component come from H2 regions. Yeah, it's a good idea. Yeah, it's just that the high resolution observations are rare. Yeah.
Yeah. Okay. Thanks.
Yeah.
Yeah, I think Hermod taken away my question, so I will not ask any more. So anyone else? I don't see any hand. We're also well past the scheduled time. So yeah, thanks Renbin. If anyone else have questions, then please forward it to Renbin directly. If required, I can provide the email address. I hope Renbin is happy to take the questions or email.
Yeah, of course. Yeah.
All right, let's thank everyone. Let's thank Renbin. Yeah, have a good.
Okay, thank you for your attention. Thank you for inviting me. Bye-bye.
Bye-bye.